2.6 Nonlinear Inequalities. If f of x is a polynomial function, then a polynomial inequality has the following form. So either f of x could be less than 0, f of x could be less than or equal to 0, f of x could just not be equal to 0, f of x could be greater than 0, or f of x greater than or equal to 0. So if you think about it, it's like all those different ways that they aren't equal, but it's showing some kind of relationship. So we've got greater than, less than, any of those things. So the inequality f of x less than 0 is true when f of x is, now think about this, f of x is the same thing as y. So if we're saying y is less than 0 is true, then f of x is negative. So that would be the part of my graph that is below my x-axis. And if we're saying that the inequality f of x, so again, f of x is y, so if y is greater than 0, it's true when f of x is positive. So first we're going to look at just a graph itself, and we're going to think about all these different kinds of inequality ideas. So if I am considering this graph of a function, first thing I'm going to do is translate it to a number line. And all these points that are on my graph here are going to be called my critical points. Now, those are the things that I want to plot on my number line. You don't have to make this number line plot, but I really like the way it kind of guides your thinking. So here's 0, 2, 5 is a 0, so all the zeros I'm plotting, -2, and -4. And I'm going to label them. I put 0 on here, but it's not actually a point. So if I think about it, when I look at this graph and I am looking at when x is -4, if I go to the left, my y is positive. So I'm going to write a plus sign here. Between the -4 and the 2, my graph goes down, so it's negative. Between the -2 and the +2, my graph's going up again, so this is, my y is positive here. And then between 2 and 5, my graph goes down again, so it's negative. And then it looks like I've got a tangent point here, and it goes back down, so still negative. So now I'm going to use this number line kind of thing that I have here to really think about where all these different things are happening. So first it says, where is f of x less than 0? So where is f of x negative? Well, it's negative from -4 to -2, -4 to -2, union. It's negative from 2 to 5. It's 0 at 5, but I don't want to actually include that 0, right? I just want to include up to it and on the other side of it. So from 2 to 5, and then from 5 to infinity. And it might help to have a negative infinity out here and an infinity on the right-hand side. Where is it equal to 0? Less than or equal to 0. So now we could say from -4 to -2, but now I can include both of those. So hard parentheses. And now I can actually include the 5 as well, because that's when it's equal to 0. So now I have from 2 to infinity. 2 would be a hard parenthesis, infinity would be soft. So now we're looking at just equal to 0. So that's going to happen when x is all those different critical points, which are my real zeros on my graph. So -4, -2, 2, and 5. When is my graph greater than 0? So from negative infinity to -4, and I don't want to include that -4 because that's where it's equal. So soft parentheses, union, and then from -2 to 2 also. And again, soft parentheses. So last one is, where is it greater than or equal to 0? Well, it's greater than or equal to 0 from negative infinity to -4, but now I'm going to actually include the -4 because at -4 it's equal to 0, union. And then I have from -2 to 2, and again, I've got to use those brackets. And this one's kind of interesting because it's actually equal to 0 right at 5. So we're going to write 5, 5. which is kind of a weird way to show that. So you would not have to necessarily translate your graph into a number line, but I think that's going to be helpful for a lot of people. I normally would skip that step myself, but either way, however it makes sense to you, we're going to have some kind of graph. So for 2, we're asked to find when this quadratic is less than 0. So we're basically always just going to make it equal to 0 and solve to get those critical points, those real zeros. So we're going to set equal to 0 and solve to get our zeros / critical points. So x squared minus 4x minus 12 equals 0. And then we'll go ahead and factor. And then we'll solve. And then if I'm thinking about a parabola shape, this is positive, it's squared, so I know it's going to go up, and it's going to cross at -2 and 6. So my parabola will look something like this. I guess I also know the y-intercept to be -12, so it's not a very accurate graph, but we're looking for a quick sketch here. So then to translate this to a number line, and I'm going to plot -2 and 6, because this is greater than, less than 0, but not equal to 0. I'm going to make open circles at these two. And then I want to think in each of these regions, what are my y's doing? Are they positive? Are they negative? What's going on? So from the -2 to -infinity, my y's are going up, so it's positive. Between -2 and 6, my y goes below the x-axis, so it's negative. Then it goes back up again, so it's positive. So if they're asking me when this function is less than 0, they're really saying, when is f of x less than 0? Well, it's less than 0 between the -2 and the 6. So in interval notation, that would be -2, 6. So remember, our interval notation is always telling us like the beginning and the end of the x where something's happening, right? It's telling us where on the x is our y less than 0. That's what we're showing right now. So the next one, we have a higher degree polynomial. We've got 3rd degree here, and it's positive again, so I know that the shape will be something like this. So I'm going to keep that in mind. Again, that's positive and degree 3. So we always want to have that shape in the back of our minds. We want to have everything on one side and 0 on the other again, so I'm going to subtract the 3x squared, add the 24, so we'll have x cubed minus 3x squared, we're putting it in descending order, minus 22x plus 24. And then remember, we're always going to set equal to 0 and solve. And I can see no kind of pattern here that will help me factor. I cannot factor by grouping here. And so I'm going to have to look at my p's and q's. So q would be a factor of 1, so my denominator is just 1, but my numerator could be plus or minus 1, 2. I'm looking at the 24 and factors of 24. 3, 4, 6, 8, 12, or 24. So we'll go ahead and start with 1. We might get lucky. Writing out my coefficients. Well, look at that. We already have our first 0. So then I want to look at the resulting quadratic and see if I can factor. And it looks like I can. X minus 6 times x plus 4. So we can solve that to get all of our zeros. So our zeros are 6 or -4 and 1. Don't forget about 1. So when I graph, I already know the shape and I need to plot -4 and 1 and 6. Okay, and I also know I have a y-intercept of 24. So I know that I go through at -4. And then I need to go back down through 1 and then up through 6. So our graph looks something like this. So again, what I'm really interested in though is where are the y's positive or negative, like what's going on. So I take all my real zeros and I translate them to a number line graph. And this time it's or equal to, so I'm going to make these solid filled in dots. Again, you might be able to look at the graph up above and do this, and that's fine. But I think this is really helpful for some people. So I'm going to model it now. So when I am to the left of -4, as I go to the left, it's down, so this is negative. Between the -4 and the 1, my graph pops up above the x-axis, so it's positive. And then between 1 and 6, it's back down, it's negative. And then after the 6, it goes up again, it is positive. So this is my, my signs for y. But now I wanted to know, if I go back to the beginning, it says, where is my function greater than 0? So that means I want my f of x to be greater than or equal to 0. So where is that happening? Well, it's greater than or equal to 0. My y is greater than 0 where it's positive. So from -4 to 1. And I'm using brackets because it's or equal to, I'm including those numbers. And from 6 to infinity. So next we're going to look at rational inequalities. So we're going to do those in a very similar manner. We're going to graph them, but now we can change signs at real zeros and at points of discontinuity. So these are going to all give us our critical points. Before, our critical points came just from our real zeros. Now it comes from real zeros and discontinuity. So remember, our real zeros come from the numerator equals 0. And the points of discontinuity are really from our vertical or x asymptotes. And that's when our denominator equals 0. And maybe we should add up here that this one's x-intercepts. So rational inequalities have like an extra piece. We're not only looking at our real zeros, we're also looking at our asymptotes. So we'll go ahead and start with another example. So on 4, we're asked to solve. We're comparing a function to 0. I need this to just be one fraction. I know how to graph it when it's one fraction. So I need to put these together. That means I'm going to have to get a like denominator. So I'm going to keep the 3x plus 4 divided by x plus 2. And the 3 I will multiply top and bottom by x plus 2. And it's still greater than or equal to 0. So then we'll put it together. We'll have 3x plus 4 minus 3x minus 6 all over x plus 2. And then we need to put our, let's see, 3x minus 3x, that's gone. 4 minus 6 would be -2. All right, so now what we're really doing is we're graphing f of x equals -2 over x plus 2. So that's really what we're doing now. So we need to go through all of those graphing steps for a rational function. So my x-intercepts come from the numerator. -2 cannot equal 0, so there are none. My y-intercept is when I let my x equal 0. So -2 over 0 plus 2 is -2 divided by 2, just -1. My x asymptote comes from my denominator. So my denominator would be x plus 2 equals 0. So x equals -2. And for my y asymptote, it is bigger on the bottom. That is the degree. On the bottom, I have x to the first power. Numerator is just a constant, so it's bigger on the bottom. That means y equals 0. So now I want to go ahead and put all of this together. Here's my axes. Asymptote at -2. Asymptote at y equals 0. And then for my graph, I actually have no x-intercept, but I have a y-intercept at -1. So that's going to tell me how my graph goes, right? Graph's going to be like this and like this. So now I'm going to translate this to a number line. So it turns out there's no x-intercepts. All I have is that asymptote, so that's going to be my only critical point. And it doesn't matter that it says greater than or equal to 0, because I can't actually ever equal that asymptote. So it's going to be an open circle. So we're going to have just an open circle at -2. And I can see that my graph is above the x-axis. It's positive. From -infinity to -2, my graph is up, so it's positive. It's above that x-axis. And then from -2 to positive infinity, my graph is all below the x-axis, so it's negative. So now I am asked to figure out where, let's see, I wanted my function to be greater than or equal to 0. So I'm thinking now about when is my f of x greater than or equal to 0, and that is going to be from -infinity to -2. So for our last math problem, I need to first need to get a 0 over here. We need a 0 here. So let's go ahead and subtract 3 on both sides. And then while I'm at it, I also know that I'm going to have to put my fractions together. So it'll be 3 times x minus 2 over x minus 2. So let's see. I'll have x squared minus x minus 11, and then distribute that minus, so minus 3x plus 6 all over x minus 2. Put our like terms together. X squared minus 4x minus 5. And I'm even going to factor, just always checking for holes. Numerator would be x minus 5 times x plus 1. So I am definitely going to now just let f of x equal that fraction, that rational function, x minus 5, x plus 1 over x minus 2. And we're going to go through all those graphing steps. So my x-intercepts come from the numerator. So I'll have x minus 5 times x plus 1 equals 0. So my x-intercepts are 5 or -1, or 5 and -1. My y-intercept I get by putting in zeros for all my x's, and I would actually use unfactored form for this. So I'll have 0 squared minus 4 times 0 minus 5 over 0 minus 2. So just 5 halves, or 2 and 1/2. My x asymptote comes from my denominator equals 0. And my y asymptote, I have to pay attention to the degrees. And it has a bigger degree on the top. The numerator is x squared. My denominator is x to the first. So because it is bigger on top, there is no horizontal. But because it's 1 degree bigger, we will have a slant. We have to divide it out. So we're going to have to take x squared minus 4x minus 5. So x squared minus 4x minus 5, and we're dividing by x minus 2. So I'm actually going to do this with synthetic. So to divide with synthetic, instead of x minus 2, I use 2, and then 1, -4, -5. So I'm welcome to use long division, and sometimes you'll have to, but I don't have to here, so I'm not going to. And then we ignore the remainder. It's just this part. So if I started out with squared, it's a 1x minus 2. So y equals x minus 2 is our slant. So now we need to put it all together. Here's my axes. X asymptote at 2. And then we have the x minus 2, so here's -2, and a slope of 1. All right, what else are we missing? Now we need to do our intercepts. -1 and 5, and a y-intercept of 2.5. All right, so I'm going to have a graph that goes through here, and I'm going to have a graph that goes through here. So now to go ahead and break this down to a number line graph, which I think is almost more important with these rational functions. I think these are trickier. So my critical points are everything, all my zeros and my asymptotes. So my critical points here would be not the 0, but the -1. And I think this was or equal to, right? Or equal to. So I'm going to fill in the point at -1. And then at 2, I'm going to leave it an open circle because it's an asymptote, so I can never equal 2. And then 1, 2, 3, 4, 5. I also have at 5 another 0. And I guess I don't really need all the tick marks in between. Really, this would be a much cleaner graph if I didn't have any of them, right? So maybe we should just do it like this. So at -1, open circle at 2, filled in circle at 5, and then remember we have -infinity and infinity to my left and right. So now I was being asked about my function, and I have to go through and do the plus or minus. Let's see. So from -infinity to -1, I'm down below my x-axis, so it's negative. From -1 to 2, my graph is up. And then from 2 to 5, so from here to here, my graph is down again. And then it pops back up above my x-axis again. So these are kind of weird that when you do the rational functions. I think they're a lot more difficult. The number line graph really helps. So now I'm looking for where that function was, I believe, less than or equal to 0. So let's just check that really fast. Yes, function is, we see it right here, less than or equal to 0. All right. And so that means from -infinity to -1. And I can include the -1 because it's or equal to, and I can actually equal -1. And then it's also negative from 2 to 5. But remember, the 2 has to be a soft parenthesis because it's that asymptote, so we can never equal 2. But 5 would be a hard bracket again. So that's it for our 2-6 notes.